I have a senior, but I have a few electrical students. But it's neural networks. It's a class here at SMT. It's open for seniors, even though it's graduate course. But I see a few seniors there. It's too high, but anyhow. Uh,
Philosophy of AI semester you're going neural networks. It's really interesting stuff out there.
yeah. Actually, many of my courses are from computer science, not from here. I should have enrolled in computer science. I just took one power course here.
How's it going, Mr. Byers?
Good. What's new?
No, I'm not. It's just got done making that about 5 lines. Yeah. Digital communications project one, where they had me like create music, MATLAB. So I kind
So, like, are you taking additional liberty to make it better, or is it just that complex?
I'm not really sure. It was the only way I could get it to like, I guess, sound correct. He wanted it to sound like a car. So that's the majority of it. Was trying to make it sound like a car. So I was strumming the back and stuff on it. But then I wanted to be able to switch from standard tuning to I didn't take a case. And then I had to be able to determine what it was to set out how to make a function based on so I like string one red you know like plug that into like a matrix. It's pretty hard right now. So I don't know how the rest of that. It was. Even up to today.
He's not
working
class.
There was like 5 other guys.
Today's like 10 a.m.
I got it. There's no wings.
For 2 days with me, I did 8 straight hours of class.
You know,
How's it going on?
honestly, it has the nicest chair. Yeah, I'm always just curious how I said someone's gonna talk. Yeah, go ahead. Yeah, I like questions more than answers.
All right, everyone. Let's get started with attendance. So, I think MSU people can hear me now. So, MSU people, type in the chat MSU so that I take your attendance by the end of the class. Regarding the lecture, so can someone remind me what we have talked about last time, in our last session? Something about the difference between the real and the reactive powers. We've gone through a number of powers that they have all quite similar names, but they have different functions or significance. So what's the difference between the real and the reactive power?
Real powers don't work. The real powers pertaining to like the energy.
Okay, it's the actual absorbed power that we pay for. So what about the reactive power?
Reactive power doesn't have an average component to it.
Okay, so what's its job in the system then?
Um, treated as a loss, right?
No, it's not a loss. It's some sort of power which is circulating, and its advantage it just means for the power quality, to improve the power quality. So let's say we had a voltage dip. The voltages typically here should be around 110. But if I'm transporting that voltage through certain distance, like from here to Kansas, the received voltage could be 108 or 107 because of the losses through the transmission lines. So I would need a reactive power source to deliver some of that type of power to restore the voltage to that level. This is the only purpose of reactive power. So we should consider that in our calculation, but typically we don't pay for its cost. We just get charged in our bills absorbed power or the utilized power, which is the active power. Here they made this explanation for you in details. So now we'll move forward into the complex power. So previously we have mentioned a lot of things about the voltage phasors and the current phasors. And here we see the representation as V equal V magnitude and the angle gamma for voltage, and for the current, we have I equal to I in bold and the angle beta for the current. So, and we have seen that we defined P as VI cosine gamma minus beta, and Q is VI sine gamma minus beta. I hope everyone reviewed those at home before coming in. So what did we call gamma minus beta? We had a name for that angle. Can anyone remember? It's called?
Power factor.
No, the power factor is the cosine, the whole thing. Yeah, it's the phase angle. We call that difference is the phase angle. Typically, most of the times, the angle beta would be zero, so we just take the cosine for gamma. But in some cases, we might have an angle for the current, so that would make a difference. So now the complex power is the type of power which joins those two together in a single component, and it's defined as S, which is equal to I VI star, where if we go through the explanation, we multiply those two by each other, and then the only change that we need to make is on the angle of the current. So if it was like 30 for I star, let's say it's 1030. It's initially 1030. I star will be 10 minus 30. Okay? So effectively, we are negating the current angle to obtain our complex power. And then eventually we'll get this representation of VI cosine gamma minus beta plus J VI sine gamma minus beta. And again here, gamma minus beta is the angle between the voltage and the current. So S, the complex power, is of the form P plus JQ. And its magnitude is VI, is called the apparent power, okay? And its unit is, I think this should be easy. What's the unit of the complex power? If I'm just multiplying voltage by current. Volt ampere, yeah. It's just a very easy thing to remember. The unit is VA. So now we have watt, we have var, and we have volt ampere. We should be aware about those three units. And we mentioned again the power factor calculation and why it's important. So now we need to move forward to get into the load convention. And to the generator convention. So normally, what does the load do? What's a load? Can you give me some examples of loads, of electric loads?
Anything with impedance, so resistance, inductors, capacitors,
Okay, the generator has some impedance.
motors.
Okay, but there's something specific about loads. They consume power. Okay, this is the most salient characteristic of a load. Other than having impedance or capacitors, or no matter what are the physical components, a great or a salient characteristic of a load is a unit which consumes power. This is the difference between that. Actually, the motor is one of those because it consumes power and it gives you out some mechanical power. The difference regarding to the generator is that the typical way of a generator is providing power, giving out power. So this is really a very important difference between the two in calculation. So here they are making some explanations whether the power will be positive or negative. And that determination should be dependent on whether that equipment is absorbing power or generating power. So let's start with the load. He's saying here that we have this unit, which is a load, V plus minus. And then it's important to see, let me connect those so that they seem connected in some way. And then we see the current is flowing into the load. But there's something important here. The current has to flow through the positive terminal of the load. Otherwise, it will be, instead of absorbing power, it will be delivering power. So we should be aware about the current direction. If you see below the generator convention, we see the current is coming out of the load or the unit or the structure. You can see the difference in that element. So if Q is positive, if P is positive for the load, it means that positive real power is being absorbed. If Q is positive, then positive reactive power is being absorbed. If P or Q are negative, that it means that they are being delivered by the load. And this is not very common. Typically, for loads, we'll have positive values, and they mean that the power is being consumed by them. If I tell you the power for that load was minus 100, it means that they were delivering power by some way. Let's go to the generator to see what's happening there. We see that the current leaves the positive terminal of the circuit. If P is positive, then it means here the power is being delivered, not consumed. They are opposite to each other. While if Q is positive, then it means the reactive power is being delivered. Could we see the difference between the two? So if I give you a generator and I tell you P was equal to minus 100, what's happening there? You'll tell me the power is being actually absorbed by the generator, which is not a good thing. That means that It's either a starting condition or maybe some fault is happening there, so the power flow is reversed or so. So let's take note of those two things. So normally, without even looking into the graphs or the plots, we should have an understanding that for the load, whenever P and Q are positive, that means that the load is absorbing the power. But for the generator, whenever those values are positive, that means that the generator is delivering that power. I think here there's a similar explanation to what I said, and we have some example. A single phase voltage source with V equal, so let's say here, MSU people, like every time, if you feel that I'm having a moment of silence, immediately inform me, okay? Because I'm not looking into Zoom. So, for example, 2.2. Let's say what's going on there. I think we need to make some calculations here to determine whether the power is being delivered or absorbed. So we have a single phase voltage source with V equal to 100, 130 degrees. And I is 10 degrees, which leaves the positive terminal of the source. Calculate the source real and reactive power and state whether the source delivers or absorbs each of these. So, can someone remind us of the equations? Did you memorize them or yet? So, how we could go forward with this question? What should we calculate? I think we need P and Q at first, and then we look into S. So, what's P? Uh-huh. Yeah. So, actually, he made something else. He started with S. Since we have both values, he said, okay, let's calculate instead of, you could definitely do this, VI cosine the angles. Those are the things that we need, and they are all available, okay? But he made another approach. So he started with the S, and he said it's equal to VI star, and then this is equivalent to 100 multiplied by 10. What about the angle? Should I keep it 10 here or put it minus 10? Okay. So that will be equivalent to minus 500 plus 866J. So a quick inspection of that, we could see here that the P is this value and the Q is this value. And it's interesting to see that P came out to be negative. And this is not common for a generator. It should be positive because we expect a generator to be generating power. But this is what we obtained from calculations, and this is totally fine, okay? Because here there's some explanation that the source actually came out to be absorbing 500 watts. So this is the physical meaning of the minus here. If you missed your minus in your calculations, you made a big mistake, because that means that your generator is giving out power, while actively it's here absorbing power. And Q is 866 VARs. So this is an example actually of a famous machine, which is the synchronous motor. One, the synchronous motor is operating at a leading power factor. Here we could make the calculations for power factor from the angles that we have up there. So let's get it. Let's get the angle. I think alpha is 130 and beta is 10. So the angle is 120. So it seems to be a leading power factor. It absorbs real power and delivers reactive power. So the load convention is used for RLC elements, and therefore the complex power absorbed by any of these three elements can be calculated as follows. And here he's repeating those calculations that we made before for the three different types of load, the resistive, the inductive, and the capacitive. And the only thing that we really need here to make sure of is that the impedance value is changing from one load to another. So you have the V, there's no change on the V values. As you can see, it's V gamma. But the difference is on the I star calculation, because typically we divide for the resistive load V by R. This is the easiest thing, and the angle here is negative, minus gamma of that star. Don't forget the star. So I'll just make the first example to see how we obtained that very famous V squared over R for the resistive loads. So this is the S of the resistive loads. So it'll be V I star R, and which is equivalent to V gamma times I is typically V over R. But what about the angle? The angle is gamma, but because of the star, we need to negate that, okay? And then you multiply the magnitudes by each other. So V times V is V squared over R. And the angles, you add them up. Don't multiply the angles. I don't want to see that. Okay? This is not how they work out. When you are multiplying the angles, actually you add them up. Okay? This is very important. I see too many people do this mistake. So this is wrong. Typically, you add the angles up, but you multiply the magnitudes. So minus gamma plus gamma would be a zero angle. So zero means nothing, so you could avoid adding an angle. Okay? This is for the R. Typically, for the inductor and the capacitor, it's the same thing, but the only change that we had is with the impedance, because for the inductor, we are dividing by that JXL. And here we could see on the on the output that we have plus J instead of minus J. So typically, instead of having that minus J here, he multiplied both by a J, which is typically 1. Then I had the J up there, and below it's minus J squared. And J squared is minus 1. So minus 1 times minus is a plus 1. So this is all plus 1. Then I had just a J up there. Okay? The same thing happens for capacitive loads, where we have that J XC. We take it up there, it will be minus a J. So those are really important if you want to make those calculations in the exam. If you are capable of memorizing all those equations, this is fine. Like, it's not a hard thing to know the S for a resistive load is V over R, V squared over R, and for the others. But I typically, the way I do it, I try not to memorize such things. I can do it easily like I did now. And if you were trained on that at home before, it should be something easy to calculate. I will give, for the assignments, you have definitely everything open book, so you don't need more directions from me. But for the exam, in case we have really large equations, like the instantaneous power or stuff like that, I will provide those equations in the questions. But for simple things, I believe that everyone could be capable of either memorizing or deriving them by a portion of a minute. So we'll see into that. I don't expect people to be memorizing large mathematical equations or so for the exam. So here's the conclusions. As we defined at first, that S typically is equal to P plus JQ, we need to make some comments on the outputs on the S, on the complex power of resistors, inductors, and capacitors. So, what's your observation of the output of those three units with respect to S? Okay, what about MSU people? I don't hear any of you actually. Can you make some comments on the outputs that we obtained? Well, I don't hear any comment, so I could proceed then. To me, my first observation is that the resistive loads seem not to have any Q value. So I don't see a J. It's just a real component, which is actually effectively, if you made some calculations at home for assignments and then you've seen a resistive load having a J component, that means there's something wrong there. Some added J here or there. Okay. In comparison, for the inductive and capacitive loads, they have no real component. So this typically confirms our assumptions that those type of devices do not consume that real active power. So this is important to note actually, and a very common question in case you do any interview. They would say, okay, what's the difference between those three loads? So here I made those comments here, but there's actually a difference I did not really annotate, is that the inductive and capacitive loads, they have that reactance, but one of them has a negative active reactive power and one of them has a positive one. So whenever it's positive, it means that it's delivering reactive power. Whenever it's negative, it means that it's absorbing that reactive power. So that's why now we are getting to understand why transmission lines or long transmission lines are bad, because they consume that reactive power and they lead to a voltage drop. They make the voltage to drop along the long distance. And to solve that, we need the capacitive components to deliver us that power, which is V squared over XC. So now we understand why we really need those reactive devices for power flow. Whenever a voltage drop happens, a typical thing is to put a capacitor bank on the transmission line somewhere at a certain level so that it start pumping that V squared over XC to restore the voltage to its needed level, typically 110 if you are at a distribution level. I've explained those earlier, but you could read. So here he's trying to get that magnitude of S. So we could see here from this equation, let's do math now. If I ask you for the magnitude, typically you'll get squared those two values. Is that right? That's something clear for you. And the angle, you'll get like tan. I don't like here to call it gamma minus beta because sometimes beta could be zero. But let's use what they are saying. So the tan inverse of Q over P is equal to the phase angle. Okay? Which is usually we used to call that in other books phi. So that sometimes phi could be gamma minus beta, sometimes it could be just gamma. And from there, it's a really typical power triangle. You use all the trigonometry of triangles there, making any calculation related to Q, P, and the angle. So Q will be P tan that angle. So whenever you have this angle, you could obtain Q, P, or S. Okay. So again, we need to make a difference between the power factor and the power angle or the phase angle. They are not the same. So this is the power factor. You have to have this cosine component. And you really need to memorize that. The power factor is P over S. So as you can see from here, that the Q is not needed. Q is not needed to compute the power factor. Okay? The power factor is just determined by dividing the P, which is your active power, over the complex power, which joins P and Q. So to have a high power factor, what should I have? What? I can't hear you.
High real power.
As much as high as what? It should be as close as
Professor, we can't hear you on Zoom.
strong. Can you hear me now?
Yes.
Okay. There's something wrong with those. So probably I figured out if I don't move it, typically people put it here, but I don't like to do that. So I'll keep an eye on the lights. I'll keep moving that so that it does not maybe sleep. Yeah, this is critically important. This triangle for powers calculations. So every equation I've mentioned before is listed on this triangle. So this could be enough for your midterm, maybe for a question in the midterm, not the whole thing. But let's see where all those powers will show up. So we have a right triangle, okay? If S is equal to P plus JQ, it means that P is here. I don't really need to be that smart to figure that out. And Q, because it's multiplied by J, it means there's a 90 degree. So this is Q. This is how I typically do, even I did that in my qualifying exam. So this is Q by the laws of physics. So now S, there's no place remained except the hypotenuse. And S is the sum of two things, so they should add up to that quality. So the angle that we really consider in our calculations is this one. Okay? We forget about this angle most of the time, but we could use it. So tan phi, let me call it phi, is equal to the opposite to the adjacent. Okay? So phi is equal to tan inverse Q over P. You're done. You got the angle. So, but here phi, it is gamma minus beta. Okay? And the other explanations, like P, you know P, it's VI cosine the angle, which is phi. And Q is just VI sine phi. Okay? I think we're done. So this is the very famous power triangle. And now you know the units that P is in watt, Q in var, and S is in volt ampere. So that would be very important to draw and make the calculations and show the angles. So typically you just make the angle difference here. Let's say I gave you gamma equal to 70 and beta equal to 40. So this will be like 30 degrees. And typically I need to give you either one of those, either P or Q or S to make the rest of the calculations. It can't be three unknowns, okay? So typically I'll give you like the Q value. So you make the rest of the calculations and plot the triangle. So let's solve some example now. Example 2.3. Yeah, this is very important actually. Power factor correction. So we'll make the calculations and we'll figure out in certain situation what we could do to fix the power flow or power circulation using very simple items like reactive power or so. So we have a single phase source delivering 100 kilowatt. What's that? It's active power to a load operating at a power factor of 0.8 lagging. So a good practice to write down those numbers. To see what are the missing items. Calculate the reactive power to be delivered by a capacitor connected in parallel with the load in order to raise the power factor to 0.95 lagging. So let's say power factor old is this value. Power factor new should be 0.95 lagging. Okay? So at first, we need to calculate our old Q. Okay? We have that P, we have some power factor. And then we see what should we do to pull up that power factor into 0.95. Okay? Assume that voltage source is constant and neglect the impedance between the source and the load, which means that this is V, this is here L. So there shouldn't be any loss here on the path. No loss. If we had here some resistance, this is a different story. Okay? Typically, you have a lot of resistances and reactances because they are transmitting power. So, let's begin with the calculation. So, the original power factor was 0.8. So, to get this angle, you need easily to do like the inverse of that 0.8 to get the angle, which is the cosine inverse of 0.8. If the power factor is equal to the cosine of the angle, okay, so the power factor. So this angle is equal to cosine inverse the power factor, okay? This is 0.8. So we will obtain an initial angle for the load, which is 36.87 degrees. And then from the power triangle, we would able to get the Q. So this is the angle, this is P, this is Q, this is S. We got this to be 36.87, and I have this value. Okay? So a common thing to do to say tan the 36.87 is equal Q over P. I have this value, which is 100 maybe. Then you get Q. Okay? This is given. Here he said, no, QL could be calculated by P tan phi, so it's almost the same, okay? It's 100 times tan 36.87. It's the same, okay? So the old Q, old, came out to be 75 kilovars. And the S, L, he made the calculation, which is P over cosine SL. So let me calculate the cosine. Cosine the angle is the adjacent P over the hypotenuse, which is S. Okay? So it's the same here. But he's calculating S. So he takes S here and pushes this down there. So it be S equal P over cosine. So he made the calculation, and S came out to be 125 kilovolt ampere. So let's look into the numbers. If P is 100 and Q is 75, S should be actually greater than them. If you get an S which is like 50, it means your calculations are wrong, because S is typically radical P squared plus Q squared. So it will be bigger than the biggest one of those for sure, if any other item is zero. So in the worst case scenario, if P is 0 and Q is 100, S will be 100. Other than that, it should be more than 100, for sure. So make sure of your numbers after you're done solving the question, because if I see an S of 25, this is really tragic, okay? It's much a portion of the powers. So here's a representation of the circuit. So we had this source, we had a load, and here we have some inductive component, the old one, because it's a lagging load, so it has some inductance. And our purpose here is to add this capacitor to fix the power factor. So let's get to this triangle to see what's going on. Initially, we had this big one. We had the QL equals 75. We had P is equal to 100. And we had S is equal to 125. And this is the old angle. I call it phi old. Okay? This is what we had. Now the purpose is to change the power factor. Change it in a good way, make it bigger, so that we ensure more power are being transferred into active power than the reactive one. So a typical one, like physically, if you look into that, how do you think we are able to push P to be having bigger proportion of S? Look at this triangle. What should we do? I cannot change this element. P100 is constant. What I can play with is the Q. It's either I push this down or I push it up. Definitely you should take it down so that the hypotenuse will get smaller, okay? And then the proportion of P will be bigger. Because let's say 100 over 300 is different than 100 over 200. Here it's like 50%. Here it's like 30%, okay? This is our goal. But if someone of us push this up, this is also very bad, because here the proportion will be like 100 over 1,000. So you'll make the power factor like 0.1, 10%, okay? A common thing in this class, I will definitely ask you to improve the power factor, not to make it worse, okay? So we always need to go down. How down? Depending on this suggested power factor, which is 0.95. So in an automatic step, get the inverse of this value. And then you'll obtain a new angle. It should be smaller. And then, by calculation, it came out to be 18.9. Well, the calculations matched with the theory. The angle came out to be smaller here. So instead of the old one, which was 36, our calculated angle came out to be 18, which means actually we went down as expected. Okay? So the last remaining thing is to make this calculation to get this new Q. Okay? So by angle relationships, tan phi nu, I like to call it like that, it's Q nu over P. So you make here calculation tan 18.9 equal Q nu over P, which is 100, still constant. You multiply those two, and then you obtain the Q nu value. And that came out to be 32.87 kilovars. Okay? So effectively, this is how we should do it. So we'll be removing actually from the 75 we remove those 32.87 kilovars, then we see that we reduced our reactive power by 42 kilovars to obtain a power factor of 0.95, okay, which is very good. So essentially here he's making the calculations, and I think he calculated again the S nu here. It came out to be actually a little bit, it was 125, now it became smaller, definitely, because we went down. This is definitely shorter than this one, okay? So this is also expected. And here the capacitor is delivering QC, which is QL minus QS, which is equal to 42. That's what I've calculated here. Okay? So the method of connecting a capacitor in parallel with the inductive load is known as power factor correction. This is very important in power systems. The effect of a capacitor is to increase the power factor of the source that delivers power to the load. Also, the source apparent power S decreases. We've seen that. Now it's 105. It was 125. As shown from the figure, the apparent power decreases. Okay, I've said that. And it's really good to solve the issues of voltage drops. The end result of power factor correction is improved efficiency and improved voltage regulation. To see a simulation, this is for the lab people. Actually, I contacted the person who's doing labs, teaching down there in the labs. He told me that you'll have a couple experiments on Power World. Okay, I told him this is too little, but anyhow, he does not design the course, so this is what's given. I would love to have more simulation, but typically here we are just required to teach the theory, and the lab sessions should teach you some practical work. But I'll try to make some modification if we can. So this is how they typically look like in that session. You have here certain source. This black thing is called the bus, okay? Any component like a source or a load should be connected to a bus. A bus is not a typical bus that we see. It's a unit where the power or the energy either comes in or out of that, and you could make certain measurements or connections there, okay? This is what defines a bus. So we have here a generator connected to that bus, and I have a transmission line. And then we have a load bus. This bus is a typical bus, but we have here some connections there. We have a load which is consuming 100 kilowatts, 75 kilovars, and here we have a capacitor. So typically, if you'd like to see how the power flow is changing, you see here the up and down buttons. You could play with those in Power World, just increase the capacitive reactive power, and you see changes on the power flow and the measurements at the buses. So here there's a purpose to stabilize the voltage everywhere at 15 kilovolts. You see here at the generator bus it's 16 kilovolts, at the load bus it's 16 kilovolts. This is a very ideal power system, actually. Very good. No losses. And here you could play with your generator settings or load settings. So in case you increase your load value, there should be definitely a change on the generated values, okay? Because they should be equivalent. Otherwise, I cannot provide 100 kilowatt if you are generating 50 kilowatt or 70, okay? Typically, the generator side always should be bigger so that it accounts to some losses along the transmission and distribution. So I did not hear any question from the people, either here or on Zoom. It's more like a monologue. I'm doing everything alone. I'd like to hear if there's any question from you. Yeah.
What's stopping you from just starting with finding the S instead of the angle first? have the 0.95, right? So you can just use proportions to find what.
You could do from any point. I started from there. You could, as I said, you need at least two known values and you could calculate the rest. But either if I start with P or S or Q, it depends on my own choice. So typically in such a question, you just say, make all the calculations. No matter where you start, we just need to see the final results. There's no mistake in that. So I was actually trying to solve it in a way, and I saw the book is solving that in another way, but we'll be there both. I'm not into now starting with the new section because that one's really large. I just have a note on the book. Yeah, this is good that I've remembered. And another note for MSU people. So MSU people, there's a room for you at your campus. They asked me if I need a room. I said yes. So you are eligible to go there and join the class from there online. You don't have to stick at your home. I received a message today. Someone of you had a power outage at Springfield. So in those unfortunate incidents, mainly in exams or so, we try to avoid them. So feel free to come to your campus definitely, and go to your classroom there. There's a specific room to your class. I defined that. They asked me if I need it. I said definitely we need that. For this section, where's the attendance paper? Okay. I can get it. Yeah, I'm seeing great attendance actually. So, regarding the book, I've been in contact with the libraries here, and they informed me that they have this version of the book, the seventh version. It's available on campus, and you could use it. Actually, they just have one copy of that. I had a comment on the thing, but still, this is what is available, and I think it's accessible to you. Typically, I'll try, as long as it's available, I can use the book. Typically, here, instructors can choose any book and students can figure out what to get or where. But I made some incidental check and so I've seen actually, I was searching and effectively I found a free version of yeah, this is not a complete happiness or something, but it's version 6, not 7. I went through wait, I went through the first couple chapters. They have equal number of problems, but with very slight modifications. A few questions of them, instead of like 1030, they had a value of 1230. So I still think it could be a great resource for you to have on hand because 90% or more of the problems are the same in both versions. So I could consider that to be a supportive material for you.
You consider it the main material for homework, so we can.
I'll try to make them exactly the same. Okay. So if I say problem 2.3, it should be exactly the same problem 2.3.
Okay.
There's a free version of this.
Okay, great. If you can share it with the group or the class, that would be great because I've heard many of you saying we need the book. It's available, but it's very expensive actually. But for the university side, they think since it's available on campus, we could use it. Okay? It's on reserve. You could go there, check it. It's the same like mine. So you could find this book. I made the comparison for the first two chapters. They have exactly the same problems. Very few of them have difference in numbers. We'll try to choose the same problems between the two versions for the accessibility for you, for some convenience.
Some people might find one, some people might find the other.
Okay, we're done for today.
So you gotta get your stimulation in.
Cindy, what I put, I was going, like, I already got my grade back on it. I got like full points for it, and I like.
Okay, then I'll just.
Would it be okay if on Friday I zoomed in because I have to go back home to St. Louis on Thursday night for I have to get my car inspected on Friday.
Just this time or every
Yeah,
week?
just this time.
No, it's fine.
Okay. All right. Thank you.
You too.